A sapphire glass is made up of the elements aluminum and oxygen. So an aluminum atom has 3 electrons, while an oxygen atom has 6 electrons. Thereby, when heat is applied, it is balanced by 2 atoms of aluminum and 3 atoms of oxygen. Aluminum oxide is present on the mineral corundum, which you can see, as you can see here in the most left. This is the raw form of corundum. While in the inside, it has only 2 varieties, ruby and sapphire. The ruby is the red variety, and all other colors that encompasses the spectrum aside from red is called sapphire. So it is not the most common misconception that sapphire is only blue. A sapphire or a corundum variant is made up of atoms which is structured in a HCP structure, and it's blue in color mostly because of the impurities that arises from its chemical bonding in the aluminum and oxygen bonding. It is tough, acid resistant, good thermal conductivity, very good for screens, and capable of being formed at excellent shapes and sizes. The question of how you form the sapphire glass is how do you cut it? The corundum mineral is the second hardest at the most scale of hardness, which is the next to diamond. Diamond is the only thing that can scratch the corundum surface. But in the industry today, we use the laser technology to cut the corundum to represent sapphire sheets.
Sapphire is a corundum crystal which belongs to the rhombohedral class of the hexagonal crystal system. In this structure, you can see the hexagonal crystal system made up of individual rhombohedral units. Each rhombohedral unit is composed of an aluminum ion, which you can see in the center, and it is surrounded by 6 oxygen ions, as depicted by the red dots. Every hexagonal crystal system has this axial system, 3 horizontal axes, which are the A3, A2, and A1. The C-axis is the 4th one and the vertical one. Corundum crystals has the elements of symmetry, mirror turn of axis in the 6th order or ternary inversion axis, 3 axes of the 2nd order normal to it, which are the horizontal and it is perpendicular to the vertical axis, 3 symmetry planes normal to the axis of the 2nd order and intercrossing along the axis of the highest order. And last is the symmetry center, as what you can see here. In figure A, you can see the schematic arrangement of aluminum cations and octahedral halos between 2 layers of oxygen and ions. Take note that this is only the basal plane. That's why the upper layer of the oxygen ions are not shown. A1, A2, and A3 are translational vectors of the hexagonal sapphire cell for the basal plane. In the second figure, the schematic of the packing of oxygen and aluminum are shown in the direction of the C-axis. The crystal lattice of sapphire is formed by aluminum and oxygen ions. The oxygen ions are very near with each other, forming a hexagonal closed packing. As you can see in the diagram, the yellow balls can form a hexagonal shape. The aluminum cations lie in the octahedral halos between the closely packed oxygen ions, filling 2/3 of these halos, as depicted by the yellow or by the violet circles. To satisfy valency requirements, only 1 out of every 3 octahedral sites is unoccupied, so that each aluminum ion is surrounded by 6 oxygen ions, and each oxygen ion is surrounded by 4 aluminum ions. If the radius of each is taken as a unit, then the halo contains a ball with a relative radius of 0.41. Due to the ratio of the ionic radii of oxygen and aluminum, equal to 1.40 and 0.57 respectively, the cations are located within the halos of the anion packing. They slightly distort the lattice, but do not fall outside the stability limits of the octahedral position. Anisotropic material. Sapphire is an anisotropic material. Its properties are largely dependent on the crystallographic direction in which measurements are taken. For instance, the elastic modulus, the electrical conductivity, the index of refraction may have different values in the 1010 and 2110 directions. The extent and magnitude of anisotropic effects in crystalline materials are functions of the symmetry of the crystal structure. If there is a low level of symmetry of crystal structure, then there will be a high degree of anisotropy. As you can see in this diagram, the friction coefficient is different for each crystallographic direction, and this is an evidence of anisotropic property. Instance of anisotropic property is in the measurement of Young's modulus. These measurements are based on different sources, but we can notice that each of the measurements portrays different values for various directions.
We're in the process of making sapphire glass. These are the two major processes in making the sapphire glass. We need to grow some bowls and make some super thin shields of single crystal sapphire for those smartphone displays. Growing large crystal sapphire bowls are utilized by using heat exchanger method. This method was favorable for the GT Advanced Technologies, as so they see so much convenience in making large sapphires, but it has an expensive method of growing it. But you can produce high quality sapphires and a big sapphire on this method. And this method was originated or invented by Fred Smidid and Dennis Sinichi at the Army Material Research Lab in Watertown, 1967. The process in heat exchanger step 1. A sapphire seed is placed at the bottom of the crucible. This is the crucible and there is the sapphire seed. The mixture of synthetic materials. The sapphire seed is mixed with corundum and crackles. Crackles are the byproduct of the process of Bernoulli method, a method in growing crystals. The step 3 and 4, the special furnace heat exchanger. The full crucible is then placed inside those special furnaces. Those special furnaces utilizes the heat exchanger, which heat exchanger method. The furnace is sealed and air is evacuated and is heated at high temperatures to melt the materials all together, and while keeping the seed just below its melting point by passing helium gas through the heat exchanger beneath the center of the crucible. That's why it's called heat exchanger method. Heat and vacuum help purify alumina by vaporizing some impurities that cause some discoloration, and it makes it pure. The end product is a large bowl. As you can see, this is a large bowl of sapphire crystal. A single crystal made of sapphire that large. That is very big. After partial melting of the seed, a helium flow is increased to cool the seed and initiating crystallization of aluminum into the seed. The furnace is then held at constant temperature during growth of the crystal, which proceeds out from the seed in 3 dimensions. As you can see, this is a 3-dimensional bowl. The material is put through a series of cooling cycles over the 16 or 17 days, during which time the sapphire slowly crystallizes from bottom to top. Then, after crystallization is complete, the furnace temperature is decreased by helium flow and the bowl is slowly annealing in the situ. Now, we're in the second major process, making super thin sheets of sapphire, proton-induced exfoliation, developed by GT Advanced Technologies. GT Advanced Technologies name a machine Hyperion. The process 1 is the sapphire wafer. We need to cut a sapphire wafer of precise dimensions, and that is the end result of sapphire wafer in the bowl that you cut. The Hyperion. Hydrogen ions are bombarded by this device. The Hyperion induces the hydrogen atoms in a precise layer beneath the wafer. The protons are implanted precisely inside the wafer by the Hyperion, and they penetrate precise depth inside the wafer, as you can see that. And you'll see in the next step why. Cooking the wafer to separate the the super thin sheet that is separated by the hydrogen atoms that causes the top layer, the super thin sheet, to exfoliate. End of the process, the result is a super thin sheet made by the PIE. And you can repeat that step in order to produce multiple thin sheets of aluminum, synthetic aluminum crystal display. Other polishing finishes. The super thin sheet of sapphire is then polished to increase clarity and strengthen it further. Some holes are punched out of the wafer for buttons and speaker penetrations. And the end product is this, the smartphone display. Thank you.
The performance of sapphire glass. Without its impurities that give the sapphire its natural color of blue or any other color, the man-made version of sapphire, which is the sapphire glass, is now transparent. It is grown in furnaces, cut into thin slices, and can be made into the screen of smartwatches. It is extremely hard, corrosion resistant, scorch resistant, and can withstand high temperatures. Sapphire glass has a density of 3.98 grams per cubic centimeter, which is 67% higher than the Gorilla Glass of 2.54 grams per cubic centimeter. So, for the same thickness of glass, the sapphire will weigh quite a bit more. Now, for the thickness of the sapphire glass, it is 0.6 millimeters. Comparing it to its direct competitor of Gorilla Glass, which is 0.55 millimeters, the difference is only about equivalent to a human hair, so it's not that big. And in the Mohs scale, its hardness has a grade of 9, which is only beaten by diamond, which has a grade of 10, which diamond is the hardest mineral in the world. Now, for now, sapphire glass is mainly used in Apple Watches. In using it in an Apple Watch, it has a large percentage of brightness decrease of 32%, and it also has a decrease in color shift and than other OLED materials. So it has a little bit of viewing problem, but it's not that visible. In reflectivity, the sapphire glass has a little bit higher reflectivity compared to its other competitor, which is the Gorilla Glass. For now, it is counteracted by using an AR coating, which is an anti-reflective coating, but the downside is the AR coating is susceptible to scratches. Now, these are the results of some tests and comparing the sapphire to its other competitors in the market now, which you can see it scores a very high number compared to its competitors.
And now for the applications of sapphire glass. For the uncommon uses, sapphire glass are used in aviation, particularly in aircraft aviation displays. Another is the use in optic heads of missiles and also in bulletproof glass. Sapphire substrates are also used to produce the next generation of ambient lighting, white LEDs. The future for LED lighting is bright as the world strives to be more energy efficient and less reliant on toxic elements such as mercury. The Brigadier, a smartphone created by Kyocera, used sapphire glass in its display. They claim that objects would normally scratch a smartphone display would do nothing on the Brigadier's screen. And that was correct. A well-known smartphone reviewer tested it out using coins, a knife, and even gravel. And the result, the screen seemed to be untouched at all. The only incident the sapphire glass was being scratched was when it is intentionally dropped numerous times on rocks, but only produced a small amount of scratches. Sure, sapphire is scratch resistant, but it isn't shatter resistant. Another use of sapphire glass is on the Apple Watch premium models, whereas the cheaper models use Apple's own ion exchange glass. The use of sapphire glass has been introduced since the Apple iPhone 5S. But you may think of the display. No, you're wrong. It's used on the new home button, which is called Touch ID, which is a fingerprint sensor. And also at the back, you would see it on the camera lens.